Hi everybody, this is Mr. Molikash. This is our week 9 video for Math 171 at JCC. Want to remind everybody watching this video that you can contact me with any questions at this email address. Okay, so a couple of things we're going to be looking at in section 2.1 of the Julie Miller book are quadratic functions, which when we graph quadratic functions we get a parabola, right? So we'll look at two different forms of the equation of a quadratic and how we can transform from one to another. And then we're going to look in section 2.2 at polynomial functions and polynomials, what we mean by that, and start talking about what might happen with the graphs of quadratics, but more than that, you know, maybe x cubed, x to the fourth, and so forth. Okay, all right, so let's hit the ground running. So in a quadratic function, the definition of a quadratic function is one that looks like this, where a is not 0. If a were 0, it would be a linear function, and the b would be the slope of the line, and c would be the y-intercept. It still turns out that c is the y-intercept for quadratics, but then we have this term, these individual pieces, the ax squared, the bx, and the c are called terms. There's 3 terms, so we call that a trinomial, but this is a quadratic function because the degree of the polynomial is 2. The degree is the exponent of the variable and the highest one of those, the highest variable exponent. So later on when we talk polynomials, we'll have higher degrees like x cubed, x to the fourth, and so on. Okay, so this equation, this formula, if you will, okay, is called general form. This is what they refer to as general form. You can rewrite this in a different form where you still have the same a that you did before, and we'll discuss what that does to the graph in just a moment, but you have a factored out of a binomial, possibly a binomial squared, plus some number here, right? And so the binomial is x minus h, and then this other number is k. And here, the important form here is the h and the k are the coordinates of the vertex. Okay, now the vertex is either a maximum point if the parabola is pointing down, or a minimum point if the parabola is pointing up, right? So why would it be pointing down? Well, this is what happens when a is negative, and this is what happens when a is positive. When a is 0, you get a horizontal line, y equals k, because 0 times anything is 0, so the entire first part would drop out. So you have to have a non-zero a for all of these, okay? And again, up here, if a is 0, you get a slanted line. If b is non-zero, and then here, if a is 0, you get a horizontal line. But in all of these, the a is the same. Okay, so the book will tell you how to get from this form, general form, into the bottom one, right? How to take an example, like how to take this and rewrite it as this. And there's a process that is called completing the square, which I'll go through, but I have an easier way of doing this, or what I consider to be an easier way. So in this top form, okay, the vertex is still h and k, but h is negative b over 2a. You might remember that from earlier math. The opposite of b over 2a. In fact, this is part of the quadratic formula if the numerator is not just negative b, but plus or minus some other thing, right? This is the this underneath the radical here is called the discriminant, and it's under a square root. It's the amount you add or subtract to this opposite of b to find the zeros, okay? But that's not true for h. H is just this, okay? So what is this again? This is the x-coordinate of the vertex. And so when you find out what number that is, then you plug it back in. You plug it back in to find k. So that's what h and k are. And remember that the a here is the same a that we're going to write in the new thing, okay? So what we could do when we have to write the vertex form, right? When we have to write the vertex form is we put all this here, and we put all of this when we find out what that is here. Okay, so let's go through a concrete example of how we might do that. And then I'll come back and show you how to do what's called completing the square with the same example. Okay, so let's say that we have, we'll start off with a simple example where a is 1. So we'll say x squared plus 2x plus 7. All right, right now, what do we know about this graph? All we know, excuse me, I dropped something. All we know about this graph, the graph of this function, is that the y-intercept is 7. So wherever it crosses the y-axis, it's 7. And the parabola is pointing up because a is positive 1. So it's a happy face parabola that's pointing up, and wherever it crosses the y-axis, it goes up at positive 7. But that's really all we know, right? Well, what we're going to try and find out is where the vertex is, where this minimum point is. And why is the vertex a minimum? Because this thing is pointing up, right? So that point down there is HK. And we know it's pointing up because A is positive. So, okay, let's go back and find out what H is. H is the opposite of B over 2A. What number is A? A is 1. Okay, so let's complete that process and figure out what number that is. So that's negative 1. All right, so H is negative 1. Great. What's K? K is f of negative 1. That means we put the negative 1 back into the function and figure out what the range value is. So we're going to take all our x's. The x here is now going to be negative 1, and the x here is also going to be negative 1. Okay, negative 1 times itself is 1. This positive times a negative is a negative. And then 1 minus 2 is negative 1, and we get 6. Okay, so 6 is the k value, so that's where the vertex is. Therefore, the vertex form is a x minus h squared plus k. What is a? A is 1. It's the same 1 that was up here. So we can just erase that and pretend that there's a 1 there. We don't have to write it, right? And then this says minus h. Okay, so what we want to do is minus negative 1. Well, minus negative 1 is just plus 1, right? But literally that's plus 1 because this is negative 1. So these two things that I'm pointing at are always opposites every time, every problem. That's minus, that's plus. If that's plus, that's minus. These, however, are the same thing. So k is 6. Okay. Now you can go online to, and again, whatever I'm erasing here, you know, you can just rewind in the video to see again. So I'm going to erase all that. But to know if this is right, we can always go to desmos.com/calculator, and I'll try to leave this this link in the comments below. And you know, you could graph this and graph this and see if you get the same exact graph. Really, though, we don't need to show this, right? So what we're going to do is I'm going to flip this over and we're going to graph this on the other side here where I have some graph paper. Okay, so here's some graph paper, and remember what was our formula, right? It was f of x equals x squared plus 2x plus 7, and we think that this is also 1 times x plus 1 squared plus 6. All right, so we know our y-intercept is 7. 1, 2, 3, 4, 5, 6, 7. We know the vertex was the opposite of this, -1, 6. So we're going to go -1, 1, 2, 3, 4, 5, 6. So there's our vertex, right? And we know the parabola is pointing up. Now while I'm here, I'm going to show you that right through the vertex is the equation of this line. This line is called the axis of symmetry. And it's a line that divides the graph symmetrically. In other words, whatever's on the right side of this line is also reflected over on the left side of this line. So we could put another point right here at -2, 7. And the reason I can do that is because there's a point right on the other side at 0, 7. So we can graph this parabola safely by going through those 3 points. So how did I figure that out? Well, I just reflected the point on the right side of the axis on the other side. And that's why it's called an axis of symmetry. Okay, so if you went to Desmos and graphed this, and you graph this, you should get the same exact graph both times. Okay. It's important to know also that this graph does not cross the x-axis. So when you find the zeros of this, when we try to find out where it's equal to 0, you get some imaginary numbers. So that is called the discriminant. So let's go back to the other side and see what the discriminant is. And then we'll do this, oops, sorry about that. Then we'll do this idea of completing the square. So, okay, remember the discriminant. It's spelled D-I-S-C-R-I-M-I-N-A-N-T. The discriminant tells you how many zeros there are. So how many times it touches the x-axis, right? So if it's positive, you get 2 x-intercepts. It crosses the x-axis twice. So what happens is something like this happens, right? Or maybe something like that. But it goes through it twice. If the discriminant is equal to 0, you get 1 repeated x-intercept. And so what happens there is the vertex is on the x-axis. And so it's repeated twice in the list of roots, in the list of zeros. Okay? And then the last one is when it's negative, and you get no x-intercepts. Okay? This means that both of the answers we get have imaginary numbers in that. And like the one I just showed you that looked like that, it has no x-intercepts. Okay? So if we do this for our previous example, okay, let's go back and look at that again. It's x squared plus 2x plus 7, right? So let's see if we can calculate this value, b squared minus 4ac. So what number goes here for b? That's 2. What number goes here for a? That's 1. And what number goes here for c? That's 7. So this would be 4, because 2 times 2, minus 4 times 1 times 7, which is 28. And since that's negative, there are no x-intercepts. And we could see that easily on the graph before. Okay, so that's what the discriminant is for. And this is part of the quadratic formula. Okay, so if you want to find the values of the zeros, you put that number in the quadratic formula. All right, so now there's a process called completing the square. Let's go back to the same example. Okay, now here's how I do completing the square with quadratic. So, and this is a topic that is very rich, and you can find out a lot about the completing the square process in other videos. I don't have time to cover all of that here, but if you email me, I can give you some more information about what it means completing the square. So what we want to do is we want to take this big thing, and we want to, right now we have some stuff that what we want to do is make this into something with a square, the square of something, plus whatever's left over. Let's just call this like a remainder, what's left over. So we can separate part of this out and make it k, and then whatever's left automatically factors here, right? Okay, so first off, our a is definitely 1, so what we want to do is have this kind of thing going on, right? If a is not 1, you have to factor it out before starting this process, and that's a little bit more complicated. But what we want to do is we're going to start by putting the x terms in parentheses, and we're going to leave a space here. And then we're going to have the plus 7 over here, and we're going to leave a space after that. Now, this right now is an equation, and so far this equation is exactly the same as the equation above it. There's no difference. In order for me to keep this equation exactly the same, whatever I put here has to have its opposite here, so that if I add something, I also subtract it to keep the right side the same as it was before. So here's what needs to go here. What needs to go here is half, sorry, that was terrible, half of b squared. And this is the opposite of that number. Okay, so let's go figure out what is half of b. Well, b is 2. So what's half of 2? Okay, so since b is 2, what we're going to put here is half of 2 squared. 2 divided by 2 is 1. 1 squared is 1. So I'm going to put plus 1 here. So then what has to happen? Well, what has to happen over here is I have to put minus 1, because these two numbers need to make 0. If I add extra stuff or subtract extra stuff, now my equation's not balanced. All right. So then what I have to do is I realize that this thing is going to be able to factor. I can factor this into x plus 1 and x plus 1. And if I multiply this back out, I get x squared. Outer terms is plus x. Inner terms is plus x. And last terms is plus 1. And look at that. That x plus x is actually 2x. Okay, so these are the factors. Moreover, because the factors are exactly the same, I can say that one of them is squared. So what I just did here was complete the square. And then 7 plus negative 1 is plus 6. And this is our vertex form. This is the vertex form. So if you like this process better, you can go ahead and do it. If it doesn't make as much sense to you to do this, then go back and do the other part where you find out the negative b over 2a and put it in here, and then f of negative b over 2a and put it there. Okay? All right, that's what happens, a real brief kind of summary of what happens in section 2.1. There are some applications, some real-world problems and that kind of thing. So you'll be using the Desmos calculator some. Okay, so a polynomial function is what's going on in section 2.2. So a polynomial function, okay, what you have are you have these numbers in front of x, and then you have these other numbers up here, and I'll call this n because I don't know what it is, right? It's some number. So what has to be true about n? Well, n must be a whole number. What is a whole number? Well, the numbers 0, 1, 2, 3, dot, 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 dot. 0 actually is a whole number. So you can have x to the 0, which x to the 0 is 1. So you can have just a plain number be a polynomial, right? Okay, so what if n is like 45? Then you can have other things added to it that have smaller degrees and smaller degrees. Oops. And so on and so on and so on, right? Now, eventually, what will happen is you'll have x squared, x to the 1, and x to the 0, and that's where you have to stop, right? So when you add all of these things, and all these individual things that are added together are called terms, okay? And this n up here is called the degree, and remember the degree has to be a whole number, and it's the highest one, right? N's bigger than n minus 1, whatever n is. All right, so what happens if we just have one term? Okay, that's degree 0. So degree, and then we'll put a name for this. Okay. So if you had degree 0 like this is called a constant function. And what that is just a horizontal line. Degree 1 is called linear, and that's the y equals mx plus b that you remember from your previous math. Degree 2 we just talked about is quadratic, and this can go on and on and on forever. 3, 4, 5, and so on. So degree 3 is called cubic, degree 4 is called quartic. I remember there's 4 quarts in a gallon, you know, that kind of thing. 5 is called quintic. You'll probably never need to use a quintic function in your lifetime. And there are other names for 6, 7, 8, and so forth. But you really don't need to know them. Okay, so that's what a polynomial is. Now, what we need to talk about before stopping this video is what's called the end behavior. End behavior. Okay, so the end behavior can do one of 4 things. I'm going to draw a grid here, okay? Your end behavior can start up and finish up. What happens in the middle we don't know and we don't really care about. We're only concerned about what happens on the ends. In the extreme left and in the extreme right, what's going to happen, right? So you can go up on both sides. You can go down on both sides. You can go down on the left and up on the right, or you can go up on the left and down on the right. That covers all the bases, right? Okay, what happens up here is you look at your leading term. So remember, f of x is some number x to the n plus blah, 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 right? So the leading term is the one that's in the very front with the highest degree. Okay, so this number in front, I'm going to call this a subscript n. And I'm going to call that the leading coefficient. Coefficient. Let me spell that word right here. Coefficient. A coefficient is a number that's in front of the variable. So you have your degree, your variable, and your coefficient for every single term. The highest degree of any term is the degree of the whole polynomial. All right, so the rules about the end behavior work like this. If your leading coefficient is, let me erase all this. Okay. If your leading coefficient is positive, you get something in this column. If your leading coefficient is negative, you get something in this column. If your leading coefficient is 0, well, then you go to the next one where it's not 0, and that determines what's going on. Okay. So you should never start out with a 0. All right. So what happens, why would it do this as opposed to this? Well, this is if the degree is even. And this is what happens if the degree is odd. So, for example, if we had n is 2 and this is positive, then you'd have a quadratic function that would look like the one that we did earlier in the video. But it's possible that n could be like 16, and you might have something going on like this, right? You'd have all kinds of little bends in the graph. What matters, though, for us right now is what happens on the extreme left and the extreme right. What happens in the middle takes calculus to figure out, okay? Or a graphing calculator, or both. So if n is odd, we get, and the leading coefficient is positive, you could have a line like this degree 1, or you could have a cubic function, which kind of looks like this, or you can have x to the 7th, which looks like this, right? There's all kinds of little bends in it. So what matters is that it starts down and it finishes up. And why would this happen? If you have a positive leading coefficient and the degree is odd. So if the leading coefficient is negative, then everything flips over. It starts down, finishes down, or it starts up and finishes down. So that's a little bit of a summary of the end behavior of a polynomial function. Okay, and then the very last thing is, what is a zero? We've made a mention of zeros, right? So a zero of a function is x such that f of x equals 0. So for example, if f of x is x minus 2, a 0 would be x equals 2, because 2, when plugged in, gives me 2 minus 2, which is 0, right? So it's pretty easy for linear functions to find that out. What you do is you say x minus 2 equals 0, and you add 2 to both sides, and that's pretty simple, right? But what happens if it's like the one that we had? Something like this. What's the 0 of that? Well, the way to do that is use a graphing calculator and find out where it crosses the x-axis, or you can use the quadratic formula. Now, I'm going to mention from earlier a couple of things. First off, this looks a lot like where the x-coordinate of the vertex is, or the axis of symmetry, right? But if you add this other stuff that we talked about, the square root of the discriminant, you can add or subtract from this top number, and you get the zeros. So the opposite of b is negative 2. Remember from earlier in the video that this thing under the square root was negative 24. And this is 2 times 1, right? So I'm going to continue working over here on the right side of this line. And the square root of negative 24 is, oh, whoa, how do we do the square root of a negative? Well, there's an imaginary number called the square root of negative 1 that we're going to factor out of this. And then we're going to do the square root of 24. 2 times 1 is 2. 24 factors into 6 times 4. What's the square root of 4? It's 2. So this is actually 2i times the square root of 6 divided by 2. And then each one of these up here can be divided by 2. So negative 1 plus or minus I square root 6. Wow, those are the zeros of this polynomial. How many are there? There's 2. Negative 1 plus I square root 6 and negative 1 minus I square root 6. Now, it's imaginary. These are imaginary non-real numbers. They're not real numbers. So remember, the graph didn't cross the x-axis, and this is why. Okay, this is why, because the discriminant was negative. So those are called zeros, and they're not real numbers, and kind of a mess there, but you get the idea, right? Okay, so that's kind of all we have time for. Again, don't hesitate to post in the discussion board if you're in Math 171 online, or send me an email if you need help. Have a great week.